Now I'm sitting right here in this figure 1 Tech 9. Now I want you to pay close attention to this figure. Look what this is. This is the microscopic cross-sectional area for absorption. So this is target area. And then look down here, neutron differential energy level. So this is my neutron energy level, right? So now this is essentially showing what happens to target area as I change neutron energy level. And we said all of our neutrons are born really super fast from fission. They're born way out here, greater than 0.1 MeV. And if I could slow them down somehow, I could move this way, increasing the target area. However, this region between 1 electron volt and 0.1 million electron volts, which is 100,000 electron volts, it's going to pose some problems. In actuality, the neutron, as it's traveling between these two energy levels, there's a possibility, especially on these big sharp peaks, that it gets captured. And we know that that's one of our probabilities for absorption. There's capture and fission. And if I linger around in these energy levels, I'm going to get captured, my neutron is gone, and can never come over here and be available for fission. Going to be key. So look what it says right here. The change in cross-section with energy level, it says, is often complicated. But generally, as neutron energy level decreases, goes down, the probability of an absorption reaction goes up. And the probability we're looking for is the fission probability, fission absorption. All right? Note here, I put this note in here so you do not ever forget this graph. This is the single most important graph to know and understand in reactor theory. Let's define a couple things. I said, we've got to start describing the neutron, the characteristics of a neutron. If I say a neutron is born, it has an energy level of greater than 100,000 electron volts, 0.1 MeV, that is the definition of a fast neutron. So we're just describing it by its energy level. A fast neutron is greater than 100,000 electron volts, which is 0.1 mega electron volts. That's a fast. A slow neutron is less than 1 electron volt. Big difference between the two. And then an intermediate, or another name for intermediate, we're going to call it, keep this word in mind, I know it's weird, epithermal. Epithermal is in between the two. It's greater than 1 electron volt, but less than 0.1 mega electron volts. Those are the three energy levels that you need to know forever and always. You have a neutron in your presence that's greater than 0.1 million electron volts, it's a fast neutron. That is the definition of fast. The definition of a slow, less than 1 electron volt. The definition of an intermediate or epithermal is the region right in between the two on this graph. This represents epithermal neutrons, fast neutrons, slow neutrons. Knowing these energy levels is important so that you can look and say, okay, I've got 2 mega electron volts. I know that's a fast neutron. It's not slow and it's not intermediate. I'm defining the neutron purely based upon its energy level. Now there's another term here. This is tricky. That is based upon energy level. And it is called a thermal neutron. Thermal neutron. The definition of a thermal neutron is one that is at equilibrium with its surroundings. That's key. So if I have this graph here, and here's 0.1 mega electron volts, and I have 1 electron volt, I have a neutron here. It could be at thermal equilibrium. If it's in a high energy area of greater than 100,000 electron volts, it could be thermal. But that's not usually what we're looking at. I could get a thermal neutron here. It could be in thermal equilibrium with its surroundings because its surroundings are in between 1 electron volt and 0.1 mega electron volt. But for the most part, for us, the slow region, which we know is less than 1 electron volts, is essentially synonymous, but there might be some tricky questions out there. But when our neutron is fully thermalized, when it has fully reduced its energy level and increased its target area and it's ready for absorption, it has undergone all of these scattering reactions to slow down and then increase the probability of interaction. When it's all done, it is generally much less than 1 electron volt when it gets absorbed. So it is a slow neutron, and it is at thermal equilibrium with its surroundings. Therefore, it's a thermal neutron. I have to point that out.